Hello everyone, I welcome you to my channel. This is the Bright Stars Academy where all knowledge lies. My name is Mr. Arnold, and in today's tutorial we are going to go through the introduction to calculus, and we are going to study about differentiation 1. But before we begin today's session, please give a like, subscribe and comment. Right, as this being our very first video, we need to know the kind of topics and subtopics we are going to experience as we study about calculus, and we are going to go through the introduction to differentiation 1, and this is our table of contents. Summarize, we are going to begin with differentiation from first principles, and in differentiation from first principles we are going to cover we're going to study about the linear and quadratic functions and how to also differentiate them to get their derivatives from differentiation from first principles. We are also going to talk about the polynomial functions. After covering the polynomial functions, we are going to talk about the fractional functions. Later on, we are going to cover about the surd expressions, how they express those numbers in surds, and then how to differentiate when we are given such functions. As well, from there, we are going to talk about the trigonometrical functions, and after we have covered the trigonometrical functions, we are going to also know how to deal with the implicit functions. From there, we are going to go and see how differentiation is applicable in real life today. For example, we are going to see how to find the equations of the tangents and normals to the curves of different functions. Like for example, maybe polynomial functions, it can be fractional functions, it can be implicit functions. We are going to also discover how to get the equations from there. Then from that, we are going to study about how to get the maximum and minimum. And after then we get the small changes. Later on, we shall be able to conclude with rate of changes before we go to our next session, which is further differentiation. Right about now, we are going to go through our very first lesson, and we are going to discuss about differentiation from first principles. In this particular course, we are going to learn about the four major steps in finding the derivative of the function. Now we need to understand what is differentiation. In differentiation, we usually aim at finding the derivative of the function, because we know very well that the derivative of the function is the gradient function, the function which represents the gradient at a particular point when the value of x has been substituted in at that point. This enables us to be able to get the gradient of the function, because we know very well that we have so many functions, like we have seen from our previous video. We have trigonometrical functions, we have implicit functions, and so many other functions. Now, they usually come up when the gradient at their different points are always different. But when we differentiate, we are able to get the derivative of the function, and that derivative of the function can help us to get the gradient at that particular point on the function. When we are dealing from first principles, we need to know that we have to introduce errors. That becomes our very first step. Now let us see how they come about. When we take a close look on our function here, our function that I've presented to you is y is equal to x squared, and in this function, as we observe it, we have these values y and x are variable terms. They keep on changing. When we observe very well, now when we get to know that one of the values, for example here, the value of x is a, that means that the value of y is a matter of us substituting in the value of a, and it is becoming x squared. So we are going to consider another point, but this point must be so close towards this point to assume as if that point is 1. Now when we take this other point, because in this case, in the matter of us to observe clearly, I made sure that I widen it such that you can be able to see, but we take them when they are too close to each other. Now when we take another point here, which I am pointing at, this is going to, when this is a here a plus h, that means that the value for y it is going to become a plus h, but in brackets squared, because it's a matter of substituting in the new value of x that we have got, and that's what we call introducing in of small errors. Now let us go through the steps taken in differentiating from first principles. And our very first step is what we have discussed in our previous slide, and we said that introducing or adding one of small increments, which can be small change in x, like you see here, this is delta x and delta y, or we can use this symbol which is like for a triangle, which is small change in x or small change in y. After we have done that, then we shall have to make small change in y the subject of the expression of the particular function that we are dealing with. Then when we have achieved to do that, then we shall divide the small increment of x, that is the delta x or small change in x, on both sides, such that we form small change in y over small change in x on one side. Then from there we shall have to convert using limits to convert from small change in y over small change in x to dy dx, which becomes the gradient function of that particular function. But we need to note some of the things that are generally recognized. One, that the derivative of a constant is zero. Whenever you differentiate a constant, as we shall find out when we use these 4 steps, our constant will always to be zero. Then another thing you need to know when you are dealing with these numbers is that the logic of attempt might change, but the basics fundamental steps must be respected. The logic might change due to the change in different functions that we deal in, but when we are dealing with these steps, these are the key steps in order for us to be able to achieve what we want to achieve in that particular number we are dealing in. Then another thing we need to note is that in the basics in algebra, in areas of binomial, fractions, surds, and indices, we need to know how to expand our logic in these other topics in order for us to be able to go through these challenging numbers, because we shall start with the easy and later on we shall find those hard ones. But how do we deal with them when we are differentiating from first principles matters a lot. Then lastly, let us always be careful and respect integers in every step. One of the key things that even makes the most bright students fail is that they usually undermine integers, those things of negative, positive, and they end up failing. Not that because they don't know, but because they take them for granted and they cost a lot in their working. At this point, we are going to go through our very first functions, and this is the linear and the quadratic expressions. In linear expression, now in this case, let us begin with the linear expression. When we differentiate a linear expression, like here they are saying that when a linear function is differentiated, a gradient of the function is attained since the variable term is of degree 1. Now what does it mean when we say variable term of degree 1? When we talk about the degree, we are talking about the power on which the variable term is raised. Now when we observe here the value of x in this case, it is raised to power 1. If it was raised to power 2, then it becomes quadratic because the variable term is of degree 2. Where the highest power is raised to is what determines the degree term, for those ones who are now new to that. So when we say that when we differentiate this, since it is of degree 1, this one is just going to go away, and then we shall remain with only this, because remember we said when we differentiate a constant it will be equal to 0. So that means that y dx is going to be equal to only m. That's what we are meaning, that when you differentiate dy dx in this case, you're going to get m, and where m is the gradient of the function. Actually, this is one of the unique functions whereby when we differentiate them, we usually get only the gradient of the function, because on other functions we usually get the derivatives of the functions in which we can be able to determine the gradient of the function at a particular point. Now, let us take for a close look on our function. This is how a linear function looks like. It's a straight line. It takes up this shape of y is equal to mx plus c, and this is how it is drawn. When we are going to differentiate, remember our very first steps that we discussed in our previous slide. We are going to introduce small increments, and these are the small increments. So our function is now going to become y plus small change in y, which is going to be equals to m into x plus small change in x plus c. After introducing the small increments, then we go to our second step, whereby our second step is to make small change in y the subject, and to make the small change in y the subject, we have to take y across signs, whereby it becomes negative. But remember that y is being represented as mx plus c. That is the reason why where y would be, we have replaced it with this. After making it the subject, of course, we have to first simplify before we go to another step. And when you subtract this mx is going to go with this negative mx, this c is going to go with negative c, such that our remaining expression on our right hand side is m small change in x. After then, we are going to differentiate, we are going to divide by small change in x as our other step. That other step is going to, our third step is going to cause this one to be small change in x, m small change in x over small change in x, which leaves us with m, and this side is going to be small change in y over small change in x. After that, we are going to have this like we have said. Then from there we're going to take limits. Limits are taken because remember that time I told you when you have a small point here and you have another very small point here, and then we draw a straight line passing through those small points in that particular function, we take them to be so close that the small change in x is approximating to 0. Now when the small change in x approximates to 0, that means the small change in y over small change in x is going to approximate to dy dx, which is the derivative, and small change in x is going to be approximating to 0, as you see in our next step. That means that wherever we find since there is no any small change in x in our expression on our right hand side, because when we see this side there is nothing, this one has already approximated to dy dx. That means that our dy dx is going to be equal to m, which we had just said previously that here, that when we have a linear function, when we differentiate it, we usually get the gradient of that function. I hope you have been able to understand from our previous slide the steps that we are going to undertake in differentiating linear expressions from first principles. Now I have some two examples that I want us to do together to analyze and internalize what we have just discussed in our previous slide. Here is our very first question, and they are telling us that find the derivative of the function y is equal to 3x plus 4 from first principles. Taking a close look from our previous steps, we said that in our solution that we are going to introduce small increments, and this is going to be our very first step is going to be y plus small change in y is equal to 3 into x plus small change in x plus 4. After doing that, we say that we are going to make small change in y the subject, whereby we take y across signs, which is becoming negative, and keeping in mind that our y was our function, which is 3x plus 4. That means small change in y is equal to 3 into x plus small change in x plus 4 minus 3x plus 4. When we simplify that expression further, we are going to have small change in y being equal to 3 small change in x, because negative 3x is going to go with this 3x, this negative 4 is going to go with this positive 4. After we have finished those first two steps, then we go to our very third step, which is dividing by small change in x on both sides. That means we're going to have small change in y over small change in x is equal to 3 small change in x over small change in x. That means our small change in y over small change in x is going to be equal to 3. Then our fourth step is to take limits. When we take limits, when our small change in y over small change in x approximates to dy dx, that implies that small change in x is too small that approximates to 0, because the 2 points we have taken are too close to each other, emerging to be as 1. Since we do not have any small change in x in this side of our right, that means that our dy dx is going to be equals to 3, and that means that our the function, which is 3x plus 4 in respect to x, is going to be equal to 3. Hope that you see that it is very easy. Just mastering the other 4 steps is going to help you to answer these questions. We have our second question, assuming that now this value is negative. For example, they're saying that find the gradient of y is equal to negative 2x plus 3 from calculus, using calculus from first principles. Again, they are still requesting for the same thing. In our solution, our very first step, we know very well we are going to introduce change in x. In this case, I'm using this other sign to show you that you can either decide to use delta x, or you can also decide to use small increments in that form of that symbol. When we introduce small changes in x, it's going to become y plus small change in y, which is going to be equal to negative 2 into x plus small change in x plus 3. Our next step is to make small change in y, the subject, which is going to become negative 2 into x plus small change in x plus 3 minus into negative 2x plus 3. Let us always take those negatives very serious, because they help us to answer these questions very well. Now, when we continue in our next slide, we're going to find out that it's negative 2x plus 2x are going to go away, and then we are also going to realize that this positive 3 is going to go with this negative 3, so that we only remain with small change in y being equal to negative 2 small change in x. Our third step is to divide by small change in x on both sides, and therefore here this side we are going to have small change in y over small change in x being equal to negative 2 small change in x over small change in x. To be simplified further, we are going to have small change in y over small change in x being equal to negative 2. When we take limits that the 2 points are too close to each other, that means that small change in y over small change in x is going to be approximating to dy dx, as small change in x approximates to 0. But since we don't have any small change in x this side, that means that when we differentiate dy dx is going to be equal to negative 2, which is the gradient that we saw here of this particular function. And that's how we conclude this particular. At this point, we are going to talk about the quadratic curve or expression, these functions which are in form of quadratic expression. When a quadratic expression, which is in form of y is equal to ax squared plus bx plus c, is differentiated, a gradient function in form of 2ax plus b is formed. Since the quadratic expression has a variable x of degree of 2, the gradient function would be linear as shown. What are we trying to mean when we talk about that? When we look at this expression, because of its degree being of 2, we say that the degree depends on the variable with the highest power. When the highest power is 2, that means that the function is going to have, it's going to be of degree of 2. That's why we are not considering this bx, but we are considering the one which is of ax squared, and we are saying that that is the degree of 2. When we differentiate, the gradient function we are going to obtain is going to be linear, because for it it's going to have only a degree of 1. Now, how do we correspond with this? When we differentiated the linear expression in our first slides, we discovered that we get a function, we get a constant. But when we differentiate now, in this case, this one, we are getting a linear. That means that whenever we differentiate, we usually get a function whose variable, that function whose variable is less than, the gradient function is less than by 1. Now let us find out whether it is true. Now when we take that this is our function y is equal to ax squared plus bx plus c, we say that our very first step is to introduce small increments. Therefore, it's going to become y plus small change in y is equal to a into x plus small change in x, which is squared, plus b into x plus small change in x plus c. We say that our next step is to make small change in y the subject. That means that we are going to have our expression. Now, when you expand this expression with the knowledge of perfect squares, and later on multiplying with this a across all the expression inside, we are going to have your function as ax squared plus 2ax small change in x plus 2a into small change in x squared. Then also when we expand this one, we're going to have bx plus b small change in x plus c minus this y that you have taken across sign, which is in form of ax squared plus bx plus c. When you further simplify, you're going to realize that this is going to become negative ax squared, which is going to go with this one, which is positive. This negative bx is going to go with this one here. Then this c is, which is negative, because it's going to pick up this negative, it's going to go with this one, which is positive, such that our final expression is going to appear as small change in y being equals to 2ax small change in x plus b small change in x plus 2a into x squared, a small change in x squared. When we go to our next very other slide, we're going to carry out our third step, which is dividing by small change in x on both sides. So at this side, on our right, on our left, we have small change in y over small change in x being equal to, on our left, as 2ax small change in x plus b small change in x plus 2a small change in x squared over small change in x. When we simplify further, we are going to have small change in y over small change in x as 2ax plus b plus 2a small change in x. Then that leads us to our third step, where we take the points to be too close. When we take them to be too close, that means that small change in y over small change in x is going to approximate to dy dx, as any of the small changes in x approximate to 0. That means that anything that is attached by small change in x is going to be eliminated, and in this case we are going to eliminate 2a small change in x because of this small change in x approximating to 0, such that our final the function that we have obtained, which is dy dx, which is our gradient function, and our derivative at the same time is going to be equal to 2a x plus b. And this is our function that we are talking about. It's in this form when we draw it, and when we take the 2 points, as we said, that's exactly what happens. Right about now, let us go through examples such that we see that the steps that we have just discussed through in our previous slide that can make sense to us. Here is a question where they're telling us that find the gradient function of the curve y is equal to 4x squared minus 5 from first principles. Remember, what qualifies this one to be a quadratic expression is that it is of degree of 2. It doesn't matter whether it has the other b or c, but as long as it has this x squared, that means it's our quadratic expression. So in this case, it has come in that form. What do? We follow the steps that we have just previously talked about. We are going to introduce small changes, so small increments. That's so that our function becomes y plus small change in y is equal to 4 into x plus small change in x squared minus 5. Afterwards, we are going to make small change in y the subject by taking this y across signs, such that our function, when we expand by perfect square and multiply fourth route, it's going to be 4x squared plus 8x small change in x plus 4 into x small change in x squared minus 5, then minus y, which is in form of 4x squared minus 5. Then afterwards, we are going to simplify further, whereby this is going to be negative, it goes with this one which is positive, and then this is because of this negative, it's going to multiply this negative to become positive 5, which is going to go with this negative 5. Then our expression is going to be small change in y is equal to 8x small change in x plus 4 small change in x squared. Afterwards, we are going to divide by small change in x in our third step, whereby we are going to have on our right as 8x small change in x plus 4 small change in x squared divided by 4, which later on is going to turn to be small change in y over small change in x is going to be equal to this small change in x is going to go with that side, we have 8x, then it's going to reduce this one by 1 such that we have 4 small change in x. Then our next step is to take these 2 points to be too close that they merge as 1, such that our small change in x over small change in y approximates to dy dx. And that means that since this one has a small change in x, it's going to cancel out. Then therefore our function is going to become our small change in y over small change in x is going to be equal to 8x. Now when you pull out here a 2, it's going to be like 2 into 4x, like how I told you that this 2 here is just going to drop here and to multiplies this. And that's what you are seeing. That's why our answer is in that form, which is in the other expression that we just discovered. Let us look at our next example and find out whether the steps are the same. And they're saying that what is the derivative of the curve y is equal to negative 2x squared plus x plus 3 from first principles. Our very first step is going to introduce small change in x such that our function becomes y is plus small change in y is equal to negative 2 into x plus small change in x squared plus x plus small change in x plus 3. Then our next step is going to make small change in y the subject by taking this y across signs. When we do so and try to simplify using our knowledge of algebra, we're going to have negative 2x squared minus 4x small change in x plus 2 small change in x squared, then plus x plus small change in x plus 3, then minus the y that we have taken across signs, which is negative 2x squared plus x plus 3. Following those small integer rules and also algebra, we are going to end up having this becoming positive 2x squared, which cancels with this one becoming negative x, which goes with this positive one, negative 3 going with this positive 3, such that our expression becomes small change in y being equal to negative 4x small change in x plus small change in x, then plus 2 small change in x squared. Then our next step is to divide by small change in x such that our function becomes negative 4x plus 1, then plus 2 small change in x, because this one is going to reduce this one off, also this, and also reduce this one. That means that when we take limits, small change in y over small change in x is going to approximate to dy dx as small change in x approximates to 0. That implies that anything that has a small change in x is going to be eliminated, because it's going to be taken that small change in x is 0, which whereby 2 times 0 is going to be 0. That implies that our dy dx is therefore going to be equal to negative 4x plus 1. Which is again in the other form. If we are going to remove here a 2, it will look exactly how we discussed it previously. Last but not least, we want to end by talking about the polynomial expressions. A polynomial function is one with higher powers of the variable term. What are we trying to mean? When we talk about a polynomial, is that one which can be in form of ax power n plus b x power n minus 1 plus then plus c. When you experience expression whereby their powers are more than even 3, 4, the n can be 1, 4, 5, 6 or whatever, bigger than that. That means that that is going to become a polynomial function. Even a quadratic function, actually it's a polynomial function, although its degree is so less that it is nicknamed as a quadratic function. Even a cubic function is a polynomial function because it has higher powers. But just that for them they have specific names on which we know, and we also understand the word polo means many. That means that you have degrees that are very high. Now, how do we deal with such functions is what we want to discover now. When differentiating a polynomial function, y is equal to ax squared, which we can see in this form, you are going to obtain a derivative whose variable term is raised to the highest power n in this form as n ax n minus 1, and that also happens to all the other variable terms. What are we trying to mean? That in this case, if you have another variable term attached on that particular function as in this form, that means that you are going to drop this power here, which is n minus 1, and then we shall multiply it onto this bx, then raise it to this n minus 1 but subtracted by 1, which makes it to become n minus 1 minus 1, which is n minus 2. Hope you are getting what we are meaning, although we are going to do it from first principles, and later on we shall show you how that formula comes about. Therefore, deriving this expression is going to give us this form, which is what we talked about previously here. Now, in order to solve polynomial functions, we need to know the knowledge of binomial expansion, because without the knowledge of binomial expansion, we cannot be able to know how this formula comes about on solving it from even first principles. Then, the first steps we need to know that they still apply here perfectly. The other first four steps that I showed you in the other previous subtopics. At this juncture, I want us to go through this example that represents polynomial expressions. And this is our question, and they're telling us that find the derivative of the function y is equal to 3 cubed plus 2x minus 3 from first principles. Keep in mind that we still apply the other former steps. We are going to introduce small changes in x. Here we are going to have y plus small change in x is going to be equal to x plus small change in x in brackets cubed plus 2 into x plus small change in x minus 3. Then after that, we are going to make small change in y the subject by taking this y across sign. When we expand this, now that means you need the knowledge of binomial expansions, as I told you when you are following this video, as we shall also make these videos for you to be able to understand how this comes about. When you expand, this is going to become x cubed plus 3x squared small change in x plus 3x into small change in x squared plus small change in x cubed, then plus 2x plus 2 small change in x minus 3, then minus the function y when it has been taken across signs, which is x cubed plus 2x minus 3. Y, small change in y therefore is going to become, after this expression, this negative x 3x cubed goes with this, and also this negative 2x goes with this positive 2x, then this positive 3 goes with negative 3. We shall have our function as small change in y being equal to 3x squared small change in x plus 3x into small change in x squared plus small change in x cubed plus 2 small change in x. When we divide by small change in x, it's now going to become 3 small change in x over small change in y being equal to 3x cubed, because this small change in x goes with this small change in x, plus 3x small change in x, because one of them is going to go, then here on the cubed one is going to go, then we have small change in x squared plus 2. When we take limits, small change in x over small change in x is going to approximate to dy dx, as small change in x approximates to 0. That means that anything that has small change in x is going to multiply it by 0. That means we shall eliminate it. This will go and that will go, such that our final expression for dy dx is going to be equal to 3x squared plus 2, and that's how our function is going to be. In order for you to understand, I would like to give you some of the questions from some of the trusted top textbooks, although there are so many other textbooks that you can use these questions. Our very first question, here are some of the questions I would like you to practice, and one of our questions is coming from J.K. Backhouse. Another book where I've got another question for you is from C.J. Tranter for A-level pure mathematics. Then I also have this one for differentiating from first principles from Calcus, whereby I want you to mainly practice differentiating from first principles. So here are the questions I would like you to practice as we conclude this lesson today. Take a moment. If you have not understood well, I would like you to repeat this video more times, often, so that you understand each and every step before you attempt these questions. In some of our videos, we shall be able to do some of these corrections, so that you have a clear look on your working and you understand whether you got the concept right. And you feel like if you have understood through this video, I would like you to give it a thumbs up. Share it to your friends who also have difficulties in these videos, in this concept, and also subscribe for more videos. I would like to take this moment to thank you, all of you, for watching this video. At this moment, I would like to share the highlights of our next video. In our next second video, lesson 2, we are going to tackle again on differentiation from first principles, and our subtopics 1 we are going to discuss about is fraction expressions. Later on, we are also going to discuss about surd expressions, on how we can differentiate them from first principles and how we can use our for rule to answer questions from first principles. Thank you very much for watching. Please share, give a thumbs up, and also subscribe to my YouTube channel for more videos, more exciting videos, and more in understanding. May God bless you, for God and my country.